Now let me talk a little bit about some classical algebra geometric transactions, which actually come later after the base of this talk was introduced. But so we'll introduce relatively new stuff before we go back to 70 years back. So the first thing that I want to mention is so the construction of Dolgachov surfaces. So, I mean, the idea of this construction actually belongs to Shkarevich and comes from arithmetics in a funny way. But so what the question was in algebraic geometry is to construct a surface which looks like a rational surface and it's not diffeomorphic on it. And so
how many points are you blowing up?
Well, it could be many, all rational surfaces look like that.
Yeah, but is there any specific number or for any number?
Well, I mean, so
or at least larger than like 8 or 9 or.
So the example that we start with was the maximum, and then later come other constructions of parallel surfaces and so on, and this number went from, so initially 9, then 8, and then with other techniques which is called rational blow downs, other constructions. So now when it comes to symplectic structure, I think that the record is 2. So things which are symplectic, I'm sorry, I apologize, homeomorphic to P2 blown up at 2 points, but not symplectomorphic. Now, I think that symplectic correct conjecture, meaning if there are things which are homeomorphic to P2, but not symplectomorphic, so it's still open. So actually there are different opinions if this the answer here is yes or no. And if this is Q1 plus Q1, I think that there were at least 4 papers that were put on the archive in the last 15 years, saying that they construct examples of symplectic manifolds.
Some exotic symplectic structure on this one.
I think it's not known. So the examples that were put on the web were really examples done by master of search tricks, that's for sure. But the way that they were done approximately is they consider, well, the simplest example is you consider a product of 2 genus 2 Riemann surfaces obviously it has the same order characteristic like this one, but it has a huge fundamental group. And then you do 8 Ludmil surgery on that, and that kills the first homology group. But actually, so this has a huge fundamental group, so it's not true that it's homomorphic. Still, I mean, the paper is this sort of details here with proposing way to do that, and also there was a different approach using symplectic X bundles, actually very related to what we'll be talking about, by Ivan Smith, trying to show that this is rigid, meaning that it's unique. So, but I don't think the answer is no. I have no opinion. So in any case, but so what started initially with the Dolgachov surface was to construct something which is homomorphic to P2 blown up at 9 points, and then not diffeomorphic to it. So now, the idea of Donaldson is really revolutionary. But actually, he will admit to you that he looked to what Milner did in 4 dimensions higher, real dimensions higher, and then that's what inspired him. And so I mean, I'll explain Milner construction after we finish these considerations. But let's look at what Donaldson did. So once again, you start with P2. So, and you take 2 cubic curves, smooth cubic curves on it. So clearly they intersect in 9 points. Generic smooth cubics. And what you do, you blow up these 9 points. And then if you do that, you get an elliptic vibration with 12 singular fibers. And so the construction that goes back to Dolgachov is to take this elliptic vibration and do 2 log transforms. In other words, do the following 2 surgeries. So you take a neighborhood of 2 smooth fibers. So you take this local disk time the elliptic curve out, and then you glue them back, but with different monogamy, so different end twists applied to this curve. And so the first one is of order 2, the second one is of order 3. So in fact, you can do any order, just when these are relatively prime, you get something simply connected, and if they are actually, if they have a common divisor, you get a fundamental group of this 4-fold equal exactly to the zk, where k is the common divisor of these 2 numbers. So now, it was in the very virtue of this idea of superiority that this will stay algebraic, and Dolgachov proved that. And so now this is a surface which is elliptic surface in the Kodaira classification. And so now it's rather clear that it's not rational because it's in a different class of the Kodaira classification. So the canonical class from negative shifts to positive, and so this shift changes the from rational to elliptic surface. The shift of the canonical class actually significantly affects the bundle theory on this surface. In the modern language, significantly affects the derived category of this surface. So I'll explain both, and of course we will return to this from modern perspective as well. So what Donaldson notices that if you consider this P2 blown at 9 points, so let's denote this by Z. So the Z topologically is a topological sum for P2 with 9 CP2 bars. And so he decided to study objects in this for manifolds, which are two-dimensional vector bundles. And so he applied a Taub-Surenberg observation, which tells you that Karen is speaking here in December, but I don't think she will be speaking about this. So that if you consider the modular space of instantons of rank 2, with trivial question number, so this thing, this modular space almost four-dimensional manifold, which is a topological sum of this sort by Taub's expanding of the net theorem, is trivial. And so the main part of Donaldson's paper of 1986, which I recommend to everyone, is to show that for this Dolgachov surface, so you also have modular space of this type of bundles. And actually, first, it is not trivial, but also it's not trivial depending of, without any dependence of the choice of the polarizations for this bundle. So I'm leaving this under the rug here, so that's the hardest part of this calculation, that independently of the choice of the polarization, this is not trivial. And and then the second part is that to show that these modular spaces are actually smooth invariants. And so that actually happened to be equal to this multiple fiber, that's an elliptic curve. And so that's what allowed Donaldson to prove that this two surfaces are not diffeomorphic due to the fact that these modular spaces, which are smooth invariants, are different. But of course, as you can easily check, the log transform leaves this homeomorphic to CP2 bone at 9 points. So the things to remember is that this surgery, this log transforms, produce a new manifold, which is not diffeomorphic to our initial manifold, but of course doesn't change the whole structure that much. So now this is indeed the continuation of idea of Müller, so who used this surgery to construct new uh, geomorphic structure on S7. So, and then of course there is not that much interesting things going on in higher dimensions due to theorem of Snell, but still that's a little bit more advanced interpretation of Donaldson's, of Milner's first work. But we can even make it more we can even put more theory on it, and that's what we trying to do, making it a little bit more subtle. And so a different way to think about this is to consider the derived category associated with the surfaces. And that is the derived category of P2 blown up at 9 points is equal to category generated by 12 exceptional objects, and that is so the following for example line bundles on P2, and then for each of these points you get one exceptional curve, and so this is what this derived category is. And now, from modern perspective, the derived category of the Doverchow surface so here's also 12 exceptional objects. But in addition, it has a category which I had a long argument with Kuznetsov, Russian, Bondel, and Orlov if this should exist or not, but it actually was proven, first in the case of surfaces by me, von Bosner, Pavel Sosna and Bjoning, that this actually does exist in the case of surfaces, and it does exist as proven later in the case of Doverchow surface. So this is a category, alpha is a category which has trivial partial homology. Has trivial K-theory. But actually, it is not trivial. So, and it is expected on approval that this modular space is nothing else it's a Donaldson Thomas modular space associated with this category. So the appearance of this modular space here is a consequence of the fact that it parameterizes certain type of sheaves on this quantum category. So, with the exception of the last part, which is partially conjectural, this is the status of our understanding of Dolgach of surface at the moment. I'm sorry, 2 that would be an inference. So now, what I would like to discuss is an approach to generalized geometries by analogy with what I have just said here. But I need to introduce a couple of more analogies, so it will remind you two more classical results in that direction. And so the first is, let's start with non-abelian Hodge theory. It's again something that was done by all these people, Donaldson, and Simpson. Kitchen first. But not generalized story. It's some Higgs bundle story. So what these guys have done is the following. So basically, they consider the moduli spaces of Higgs bundles. And so this is the moduli space of pairs P. So where E is a rank n bundle, vector bundle, and phi is endomorphism. Let me write it like that. So let's say we are on a manifold X. And so these two poles of vector bundle and yeah.
E.
Sorry. So so this modular space has a very interesting structure. In particular, it's always an algebraically completely integrable system, but so it has a C-star action on it, which acts on the second part of these two poles by multiplication by a complex number, let's say Z. And this has a fixed point. So now this fixed part, according to initially Hitchin and then to Simpson, is connected by so-called complex variation of Hodge structures. So these are Higgs bundles with very special filtration and satisfying this filtration satisfies property from Hodge theory called Griffith's transversality. So now, I mean, they look very much like variation of Hodge structures, which come from variations of algebraic varieties. And so you can ask which one of these do come from variation. generations of algebraic varieties, meaning that which one are motivic. And that, of course, is like a non-abelian version of Hodge conjecture. So I don't think we completely understand that. We know that ones which correspond to some points, meaning where this fixed part at some points are motivic in rank 2 and 3, but that's all we know until now. So now the other important part here is that so these Higgs bundles, they have special metrics on them, and all these Higgs bundles of any dimension on a fixed manifold do form a Tanakian category just because the tensor product of two bundles with Hermite-Einstein metric is a bundle with an Hermite-Einstein metric. So this tensor structure exists, and it makes this bundles, Higgs bundles, Tanakian category. So there are many other very interesting features that this modular spaces of Higgs bundles carry. So they are a powerful tool for approaching many problems in algebraic geometry. I mean, putting restrictions on the fundamental groups of projective and quasi-projective varieties. So for Hodge conjecture, as you're going to see next time around. So they have proven to be really a very useful tool in algebraic geometry, and not because of only the rich structure they carry, and you'll hear a lot of talks about this in December, but also because they really allow you to get applications. Also, they do relate with in a very interesting way with mirror symmetry. You'll hear a lot of talks about this as well. And last but not least, and so we will return to this in connection with generalized geometry. So there are recently subject of another interest. This is so-called P equals W conjecture, and which was proven by Anton Melit in full generality very recently. So, all right. So, I wanted to talk a little bit about some structure from classical Hodge theory, and that is the border algebraic cycles for this one-fourth Tate group, but I guess I'll skip that. And so let's try to move just one more algebra geometric observation, and then we'll move to generalized manifolds. So now the notion of a phantom is a notion which is rather miraculous, and so it usually appears in the cases when you have very simple Hodge diamonds, like in this case. So the Hodge diamond of the Dolgachov surface looks like that. And so, obviously, this all corresponds to the right cycle, the cost conjecture is true in dimension 2, of course, by Lefschetz. But now there are a lot of constructions that were introduced by many people after Donaldson, which actually do the following thing. So let me just talk about the Barlow surface. So I don't know this person, maybe Ludmil does. It's a lady, Rebecca Barlow.
She has a surface on her name and then she quit mathematics.
So, but in any
You don't
case,
need any more anything.
so
The surface on your name.
so the construction is something that really suggests the role of the surgeries and the phantom here. So what she does is she starts with some surface of general type, which has huge h to 0. And then what is done with this surface is a sequence of rational blow downs. So these are a sequence of surgeries which actually kill this h to 0 part, and so make this to look like a P2 blown up in 7 points. So it kills the h to 0 part. It kills a lot of the homology. It simplifies completely the Hodge diamond of this surface. And so initially, what was shown by student of Donaldson at that time, Ludmil Katzarkov. So this is homeomorphic, but which was shown by Barlow itself, but that's easy because to show that something is homeomorphic to P2 blown up at 7 points, actually, sorry, that's 9. Blown up at 8 points is you just need to compute the intersection form on the second homology, and then by Friedman's theorem, so it is homomorphic to it. But what Katzarkov did show is he computed these modular spaces for Barlow surface. And so if you put here 8, but the very same result of Uhlenbeck and Taubes, this is trivial, but so this is still not equal to 0 after you do these surgeries. And so in fact, in this particular case, it's 0-dimensional, but not trivial. And it's just 4 points, actually 2 with multiplicity 2, as the calculations later show. It's really a beautiful result using this baby Donaldson invariants, later called polynomial Donaldson invariants. And then later on, it was shown by that this derived category of Barlow has a very similar structure as the one associated with the Dolgachov surface, and I mean it's nature of the conjecture that this modular space actually is a modular space associated with certain Donaldson and Thomas type of invariants associated with this fund. So this simplifying of Hodge diamond of the by doing this sequence of surgeries, which is nothing else but so-called directional ball downs. So now this, I don't know who introduced this procedure. I mean, I traced it back to Hirzebruch, but I mean, it doesn't make much further history. Just look at what Briscoe did with his 7 spheres, and that's his interpretation. But I mean, it could be that it's Fritz who introduced this, but he doesn't get any, doesn't want any credit for that. But I mean, it's no, I think in the dimensional pole it was Hirzebruch.
Yeah, he was a student.
I see. So, but in any case, could be that it was known before. I don't know this. So, but in any case, so these surgeries that are called directional blow downs, they do reduce significantly the way the Hodge diamond of this fourfold look, and they create phantoms. That's what I want to emphasize. So now, what I would propose to do is to look at some generalized geometries from this perspective. And so now I admit to you that this was done, what I'm going to talk about now, much earlier than what we're discussing here. I mean, 40 years earlier. So, I mean, if you knew how to do surgery well in the 50s, so that guaranteed you a position in Princeton, almost. So, in any case, so that's what we're going to try to do. So I call this alternative reality approach, related to the main thing of humanity, religions, which are all alternative approach to reality. And so therefore there will be a lot of religious beliefs in what I'm going to say. So it's going to be quite a bit of a speculation, with the exception of the constructions and the Hodge diamonds which are computed. So, and some of the connections between Kerber-Milner and possibly some phantoms have been established. So the point here is the following. So now, you don't ask me to give you a reference to what I'll say now, except with this paper that is being written that I mentioned, because the literature on Kerber-Milner invariant is vast. So I don't know which one is best. I don't know.
Books,
There are tons of books in it. I mean, so technologically, the best book technologically, meaning from a algebraic point of view, is a book written by Andrew. That's right, Andrew Reich-Ranitsky. So that's,
I don't know the second name.
yeah, but this is the son of the greatest expert on German literature, obviously from Polish.
Oh, he died.
Yeah, Andrew. No, Andrew, and of course,
Really?
yeah.
Wasn't much older than us.
Uh,
It was long ago, maybe.
I'll die tomorrow, and then you'll see he was young. So, you know, full of life, but that's what it happened, yes. So, in any case, the reason that I brought Ranitsky's book is that indeed, I mean, so if you want to know some operation, and I am convinced that's true, you know, so you'll find it there. I mean, technology for all of it, but it is a book which looks like dehydrated meat. I mean, so there is no geometry. All the geometry is taken out of it, but you need some exact sequence of circuits is there. So his father, as I mentioned, Michael Ranitsky, obviously Polish Jew, was the biggest expert on German literature, and so he had this beautiful Saturday show, Literaturischen Quartet, which I was watching as a kid with a great pleasure. And but one thing that I remember is that he never accepted Günter Grass as an author, and saying this guy's a Nazi. And much later, Günter Grass admitted that he was a Nazi. He was stripped from his key from Gdansk. And, so maybe I was able to sniff him out. So, but what it would be interesting if Michael Ranitsky write a review of the book of his son. That would be an interesting thing to see.
Günter Grass wrote this book about these Turkish immigrants in Germany.
Wow.
One of the greatest
Because, yeah, it looks like, very
Yeah, I mean,
deeply hiding
That's
Nazi
your role,
story.
it's amazing.
well, I think he deserves the Nobel Prize that much. I mean, I'm not that much expert. So, in any case, now the example that we'll start looking is 8-dimensional, although from the tables that I have studied in all this Vermont theory, the 16-dimensional examples are most promising. Because the structure on the Vermeer number in that case is really rich. But so the example that we are going to look at is S7, and so we'll make it a complex manifold so that we keep the structure of the right category by multiplying of S1. So that would be our analog of P2 blown up at 9 points. So now it's rather clear what follows next. So it follows the Milner's game. So we start our surgeries here. And this produce new manifolds, certainly with different smooth structure, as Milner has shown. And so the Hodge diamond of this, it's very simple. So this is true in much bigger generality. I'm just giving you one example. And so everything else is zero. And of course, this is not a Hodge diamond in some general sense that Gil talks about. And so the question, of course, how is it obtained initially, and how do we get this Hodge diamond of this sort? And the answer is that surgery kills and creates new phenomena in the same way as before. And so, I mean, we have something really dumb, and so
the standard S7 times S7 has the same Hodge diamond.
the standard what?
S7, canonical S7 without any surgery still have the same.
Yeah.
Same.
So the question is, where is the beef? I mean, so where are all these Kerber-Milner invariants actually recorded? And then, so the I cannot say this is a clean statement yet, but so the conjecture is so that there is the following connection. So I didn't have time to introduce what the generalized surgery is. So in the same way as this Fock transform that, for example, Tolgachov, in the case of in the case of P2 blown up at 9 points, so you can do log transforms here, I mean generalized ones, and you know this can be generalized to big generality. You can find it here where you have families of log transforms depending on parameters, and I mean that gives you a lot of opportunities to play with this diamond, and of course with the this Kerber-Milner invariance. But the conjecture that is that there is a connection between log transform, generalized log transform, then Kerber-Milner invariant, and the derived category associated with this complex manifold S7 plus S1. So now there's a lot of work to be done really to properly say what is this and what are the objects here. It's going to be based on these bundles, on these manifolds. But most likely there is an intermediate object here, which is now not exactly connected with the derived category, but with something simpler. So in particular, you can define the kernel of the map from the K-theory into the, let's say, Hodge, whatever that means, of this manifold. And so most likely this kernel has additional filtration. Related to the Kerber-Milner invariants associated with this manifold. So I mean this it's almost noticed in the work by Peter Teichner. So I guess I don't know why he didn't go further, but certainly in his works with Colant and other authors, this idea kind of appears. So what I'm trying to convey here, and that this a little bit forgotten theory of not only 8 manifolds, I mean, this is like many dimensional. So as I said, this is very developed. So and I mean, the rare Milner is completed for anything you can imagine. Well, model of some conjecture, which was really actually settled only very recently by Hopkins and Ravenel. But then you can further try to explore this from this perspective. So there is a very promising case, and it's again this S7 cross S1, and that is connected with the work of Briscoe, where this Briscoe spheres, I mean, in fact, this exotic 28 structure in this case, are connected with the singularity theory and certainly very much with the spectrum of singularity that we have discussed. And then I think that in that case, you have really a good chance to make this connection between the kernel of this map, which is going to relate to the spectrum in this case, to the Milner invariant. And probably this is just a different read of what Edgar did, Edgar did 60 years ago. But so, now, as I said, to really go here, I mean, a little bit of a gauge theory needs to be developed, meaning what is the analog of all these bundles that we have mentioned here. So I mean, I assume that there are certain bihermitian structures that appear here, and then you will have some analog of this Higgs theory, and then eventually you can go down this modular space. So you don't need the derived category completely; just some modular space might be enough to look at it. So not really non-commutative Hodge structures, but non-abelian generalized Hodge structure might be enough, but that is something to be looked at. So, but even on topological level, one can actually look at this conjectural connection. So, I mean, on this very simple principle that these are very rich on structure manifolds, which have really dumb Hodge diamonds by analogy with Gogotrov and Barlow. And so, in order to really see where these invariants come from the point of view of algebraic geometry, point of view of sheaves, so you should look at, well, I mean, derived category, but if that's too hard to study, at least in some K-theory approach, kernel of K-theory approach to this situation. So now, of course, this could have very rich kernel theory, and I think that's what's happening, and maybe all these filtrations will appear there. And as I said, it is possible that people around Milner Kerver, their followers, actually have already studied this, and it would be interesting to look at this from this perspective. So that's what I wanted to say. So, I mean, I can say a little bit